the only thing is the question is not going to be plastered up on the board. Right? I'm going to have to write enough information up here for you to understand what I'm getting at. All right, so let's see. I'm gonna write numbers up here, which mean nothing to you, but they'll keep me from backtracking. So my number 1 here says elements in group 1A and 7A. So based on our periodic table, this is the old system. Roman numeral 1A is what? Alkali metals. It's that first column. 7 would be the other end, the halogens. 8 would be the noble gases, right? Because that's the octet. Okay, so these groups have how many valence electrons for each one? In order. First one, 1A, 7A. 1A, 7A. Valence electrons. Okay. You know, can you tell from the periodic?
1, 2.
Yeah,
3, 4,
right.
5, 6.
So the first one has 1 valence electron. How about the 7th group?
7.
That was too easy.
We want you to do one like that.
We love easy.
Well, hopefully we'll start slow and then pick up speed. Okay, how about this one? This is my number 2. Formation of a positive ion. Formation of a positive ion. How is that accomplished? If you start with a neutral atom, how do you make a positive ion? With just one positive charge. Think of your atom. What's your atom made of? Right. Protons and electrons, right? Neutrons don't count because they don't have a charge. But for the purposes of this argument, protons and electrons, when they're equal in number, you have a neutral atom, right?
I might be wrong, but is it when you have more protons?
Yeah.
Electrons? Is it when you have
Right. If you have one more proton than electron, you have a positive charge. How does that happen? You lose an electron.
That's when they share and stuff, right?
No, not yet. We're just talking about, we're sticking to one atom at a time,
A carbon.
right? So if you have, let's just say for argument's sake, you have, fluorine, right? Has a atomic number of 9, so it has 9 protons and 9 electrons, if it's neutral, right? So how is it? That's a bad choice. Why? Because halogens don't like to lose electrons. They like to gain electrons. So I need to pick a better example. How about sodium? How many protons does it get? I can see that far. 11. Okay. So now we have 11 protons and 11 electrons for the neutral atom. So to make one positive charge out of this, we have to lose 1 electron. Right? So if we lose 1 electron, the balance is now what? 10 electrons and 11 protons. The balance is in favor of the positives by 1. And the number of protons didn't change. You can't change the number of protons. If you do that, you got a different element. So it's all about the electrons. Okay. Let's go to my number 3. How many total electrons are present in N3- ion? So if you have an N 3 minus ion. How many electrons are there? Now look at it this way. Nitrogen atom, right? It start from neutral. It has 7 protons. That's not going to change. If it's neutral, it has 7 electrons, right?
Right.
So now it's got 3 extras.
So it has an electron
Right.
and 7 protons.
Right, it still has 7 protons with 10 electrons because it has a balance toward 3 negatives, which means 3 extra electrons. Okay? All right. Let's see. Okay. How about okay, I'll do this one. It's along the same lines as number 1, but just to see if in the past 10 minutes you forgot what we talked about in number 1. Elements in groups 2A and 7A again on the periodic table will be expected to form ions with charges of. This is slightly different. So what are the charges on these ions? Most commonly, okay, for 2A, where is that located? Second column, right?
Yeah.
Now it's a metal. Metals like to be positive.
So it's 2 positive.
Yeah. The first column was +1 because they lost an electron. Second column is +2 because they lost 2 electrons. So these ions would be 2 plus.
So then 7 would be, would that one be negative?
Let's see. I got to go back to the question. Ions with charges of. Yes. Negative what?
7? Oh.
1.
Right.
I knew that it would lose 2 electrons. That's why I said negative on the first time.
Okay. Okay. So why is this actually? Why do they want to do that?
You want to do more than that.
Yeah, they want to look like a noble gas. So the easiest way for a metal in that group to look like a noble gas is to lose 2 electrons to make a complete outer shell.
So for 7, it's like, it's just easy with 1 to gain 1. So that's
Exactly.
that's why it would, okay. I understand how it's working in my mind, but I don't want to say that loud because I don't want to confuse people.
Okay, so first group, they want to lose 1. Second group, they want to lose 2. Boron group, they want to lose 3. Aluminum in particular, it's always 3 plus charge, loses 3 electrons. On the other side, the halogens lose 1, the chalcogens, oxygen group, lose 2. Gain, sorry. Now I'm confusing. The halogens gain 1, the oxygen group gains 2. Nitrogen group, if it's in an ionic compound, it gains 3. But as you get more toward the middle, like nitrogen, carbon, especially the carbon group, it can go either way. It just depends on what it's bonded with. If carbon is bonded with another nonmetal, it tends to be covalent, it doesn't form ions. And that's true for all the nonmetals. If they're bonded to one another, then they form covalent bonds. But if you take a nonmetal and a metal together, they tend to form ionic compounds. And then the charge prevails. You can always tell how many atoms of each go in a formula by the charge balance. 1 sodium plus 1 chlorine minus 1. That's all you need, just 1 and 1. Okay. How about, let's see. Okay, we're going to write some formulas here. How about this one? 5. The correct formula for the ionic compound that might be formed from sodium and what's that one? Mhm.
Good job, son.
Thank you.
Let's see. Why can't we say R, AR for arsenic?
Yours are on.
Right, it's already taken. Okay, so sodium and arsenic. So we look, if we're given that it's going to be an ionic compound. So what's the most likely ion that sodium will form? +1. Right, minus the 1 electron. I get you. So it makes a +1. How about arsenic? Where is it located? It's in the nitrogens, right? Nitrogen group. So it's going to be -3. This would be -3. So in order to balance them, you need 3 positives to balance 3 negative. So we would write the compound like this. Okay? Just balance the charges.
Do you have to, put it in the parentheses?
That's only when you have polyatomic ions. Because polyatomic ions behave as single units. You can't break them apart. You can't change the subscripts. So if there's a charge associated with a polyatomic, like nitrate, then if you need more than one of them, then you have to use parentheses. Because that charge is distributed over the entire group. It's not localized. Okay, that's 5. We're making progress.
Yeah, I just feel like reviewing like this better than just reading homework.
Hallelujah.
Okay, let's see, how about 6? Okay. In which of the following pairs of compounds are both members of the pair ionic? So I've got to write out all choices here. Right? So we have this one. H, R was the first pair. Second pair. Third pair. And fourth pair. Okay, both members of the pair ionic. All right. So what do we have here? We got a phosphorus and an iodine. They're both nonmetals. So that's covalent. Okay, so that's not it. How about HBr? That was kind of tricky because bromine is a nonmetal and hydrogen is an animal unto itself. It's not a metal or a nonmetal. I would say that it's possibly, it depends on the electronegativity. We did talk about that. Electronegativity. We haven't talked about that. Okay. Which one has a very strong attraction for electrons? And if this one has a value associated with, this one has a value associated with the strength of attraction of electrons, then you look at the two of them together, right? There's one of them win.
Yeah, we did talk about that.
Yeah. And since you're not given that information, then you just have to assume that it's probably, or even if it is ionic, that doesn't meet conditions because we know that one's not. So we can say this one's not and save that argument till later. How about H2S and NCl3? Nitrogen and chlorine are both nonmetals. So that won't work either. And this is a similar situation to that one. Okay. We're looking for both ionic. How about lithium and fluorine? Oh yeah, that's ionic, definitely. How about water? Now, water's covalent. We know that. It's easy. Okay, so by process of elimination, these must be both ionic. Lithium and iodine, yeah. Metal, non-metal. Metal, non-metal. We're good there. So that answers the question. Those are both ionic compounds. Let's see. I'm going to keep track of time too. Lad, yes. I hope you're ready. We're going to detect chemical changes. Did I not hand that one out? Oh. Then that means I need to finish early, so we'll have plenty of time to work our way through it. That's my mistake. I know it's okay. Here we go. Actually, it's a fun lab, I think. Make it easy on myself. These are a series of I'm prepared. Okay. All right. I was checking my time. I always forget how long I have for this thing. 11 maximum. I need to finish early. Okay. Naming compounds. We did that in this series, didn't we?
Yeah.
Naming compounds. So let's see if we can name this one. Okay, first of all, what elements do we have here? Remember that one? Iron. Right, ferrum.
Is
Selenium. Okay, now that we know our names and we know the order that they appear, we have to decide, is it type 1, type 2, or type 3? Right. Type 1 and 2 are what? Metal, non-metal. Right. Type 3 is both non-metals. Right, so we got a metal and a non-metal, right? That's in the oxygen group. All right, so it's either 1 or 2. Now we have to decide, is it a 1 or a 2? How do we do that? Is it a fixed charge, or could it possibly have different charges for the metal? Where's iron located? Can you see it? Okay. Transitions. All but a couple of the transitions, actually all but 3 transitions are fixed charge.
So
Variable charge. So if it's a variable charge, it has to be a type 2. And that means that when you write the iron, you have to say what charge it is. And then we end this one with IDE, right?
that is where you put the number in the parentheses.
Mm-hmm.
That's what I was talking about.
Oh, you weren't talking about the other, you were talking about this.
Yeah,
This
it's
one.
like put the number.
Yeah. So now we have to find out what charge it is. So we need to look at our charge balance. Selenium is in the oxygen group. So it's going to be a -2 charge. Right. All the oxygen group is -2. So if that's -2, then we have a total of -6 that we have to deal with. So this has to be +6 total. That means each one of those ions contributes +3. 2 times +3 is +6. So there it is. All right, now 7. Let's see if this one has some value. Yeah. We'll give it a shot. Which of the following statements about polyatomic ions is correct? So the first choice is all have names which end in ATE. ATE ending. Is that correct? No. They're all over the map. There's ATE, ITE. Some of them even have prefixes. Hypo and ITE. Right, so that one's false. How about this one? All must contain one of the halogens. Halogens required. Is that true? Now, I just showed you one that didn't have a halogen, right? Nitrate. Okay. How about C? Negative ions are more common than positive ions. Negative, more common. Of that sheet of polyatomics, is that true? Because that's what I'm basing the question on. Negatives more common, yeah. In fact, we only have one positive out of that whole bunch. Remember which one it is?
Is it the first one?
I don't
The
know.
first one on the sheet.
Maybe. Well, alphabetical order probably is.
Ammonia?
Huh?
Ammonia?
Ammonia. Uh-huh. I always, when I think of that one, I always think of ammonium nitrate and the terrorist's best friend for a bomb. Ammonium nitrate, 6% fuel oil. The blasting camphor, stick a dynamite, make a nice big bomb. Oh, okay, so that one's true. Let's see. All carry a charge of 2. Plus 2 charge. What charges do we have available in polyatomics? Can you think of examples? Well, I gave you one earlier. Right? Here's a 1. Right? Well, here's a +1. There's a -1. Got any +2, -2s? No more pluses. How about this one? Carbonate.
The specialist or the hospital. You get coverage for emergency.
Let's see. Okay. How about -3? Oh, there's another good -2. Sulfate. How about -3? They're not as common. Phosphate. -3. I can't think of any -4s. I think that's as high as we go. But this one's false because they're not all +2. They're none of them +2, actually. Okay. Let's see. How about I should have left those up there. The formulas of okay. The formulas of sulfate, nitrate. Let's see who has short-term memory loss. And phosphate. So what's this one? Remember? SO.
30? Maybe.
SO4.
All 4, yeah. 2-. SO3, 2- is sulfite. And then there's another one. You add a hydrogen in here. It's only a 1-, that's hydrogen sulfate. Nitrate, we did that one. Gotta have nitrogen in it, right? And ATE is kind of, It's an archaic term for things that have oxygen in them.
So,
4.
Try 3. You know, 3 minus is nitrate. Nitrite. You know, 2 minus. Okay. How about phosphate? I put that one up there just a second ago. Phosphorus, of course. It's got to have oxygen in it. Right? How many of them? We'll take a vote. No, there's 4. I didn't have you memorize these, so you're going to have to use the exam will have that list of polyatomics in it. And really, the only way I can remember all these, I've been using them over and over and over again for years. So we just kind of drill in. Okay, how about this one? Which of the following pairs of ions are the 2 members of the pair isoelectronic? Okay, so we have to remember what isoelectronic means. Remember what isoelectronic means? I'm sorry?
Is it the number of gases? Because they're that.
Okay, you're remembering the examples that were used. Yeah. Not necessarily. The example we used did reference noble gases as our central point, and the rest of the ions branched from there. But it has to do with their electronic configuration. Okay, if they have the exactly same electronic configuration, then the 2 species are isoelectronic. It could be neutral, or it could be they could be all ions. Right, and the example that was used, well, okay, here we've got these examples. All right, trying to make something up when it's right here for us. These two, these 2, these 2, that. And then we've got some choices down here. More than one is correct, no correct. So what that means is we have to do all of them because they're those oddball choices. Okay, what's the electronic configuration of sulfur first, and then we'll make the ion out of it. So where's sulfur? Sulfur's in the 3rd period, right, which means I'm going to use the shorthand. So if we look at sulfur and work our way backwards over to sodium and then go back up to the next period, it would be neon, would be the core. So I'm going to start with neon as my core with 10 and then work from there. So in the 3rd period, we start with 3s and then we go to 3p. And by then we get to sulfur. So that's all we need. So I've got 10 electrons used up here. And here we have sulfur is 16 plus 2 is 18. 18 electrons. So that's 16 plus 2 is 18. So the neutral would have 16 in it. The 10 are used up in the neon core. And then we move to 3s. That's why it's important to study how the periodic table is structured, because it relates directly to these configurations. Okay, so now we have that one's full, and then we move over from sodium, magnesium, aluminum, silicon, phosphorus, sulfur. 4 there. Okay. Now we can add the other 2. Right? That's only 16. We need to add these 2 electrons because it's an ion. So if we do that, that makes this 6. There we go. Now, that is the electronic configuration of the sulfur 2- ion. We can do the same thing for chlorine. It's right next door to sulfur. So we just take chlorine. Right? 3s2, 3p5 would be neutral. And then we add 1 electron. Okay. Those two are isoelectronic. They have exactly the same electronic configuration. Okay, that's what we mean by isoelectronic. Iso is a Greek prefix that means same. You ever mess with those little, well, all girls in here, I don't know. Oh, wait a minute. Remember the little bugs that call them roly-polies? You
Yes.
touch them and they roll up into a ball?
Yeah.
Their scientific name is isopod, which means same foot. So all those feet are exactly alike. That's how I remember it. Okay, so if we do these, we don't even have to write the configurations for this one because these are in the same group, but they're on different periods. So they can't have the same electronic structure. There's no way. Right? Potassium's got an extra layer of electrons out there. So they cannot be isoelectronic. There's no way. How about aluminum and nitrogen? Aluminum 3+ and nitrogen 3-. Well, let's see. If we do aluminum, it'd start with neon. Aluminum, let's see, aluminum's 13 and nitrogen is 7. Maybe. So we got neon here with 10, and then we go to the third period, 3s and 3p. Neon has used up 10, so we got 3 more, 2 here and 1 there. But the 3+ does what? This is neutral. 3+ takes away 3 electrons, right? And they come up from the highest energy level and they work their way down. So all those 3 are gone. They're gone. That's the structure for the aluminum 3+ ion. How about nitrogen? Well, it's in the second period. So nitrogen would be, well, its base would be helium, right? So I'm pretty sure we're not going to make it from there. We'll try. So we've got 2 heliums, and now we're down to 2p, excuse me, 2s and 2p. Okay. That's 7. 1, 2, 3, 4, 5, 6, 7. Okay. But we've got 3 extra electrons, don't we? So we add those 3 out here. That gives us 6. That's a complete shell. So that looks like neon. They are. They're isoelectronic.
So it'd be A and C.
A and
More
C.
than one are correct.
Yeah, more than one are correct. I couldn't even remember my own statements. Yeah, that's right. A and C are both correct. They're isoelectronic. This one is easy to see because they're both anions, adding electrons. But these are a little more difficult because one's plus and one's a negative ion. They end up in the same place. They both look like neon. Those examples are right. They're like the noble gas. But like I said, they don't have to be. It's just, if I'm nice, I'll make them look that way. Okay. I'm moving pretty slow here. Look, I'm going to have to skip ahead to some others. Okay, how about this one? I'm going to write these compounds up here. the names of the compounds. And then the question is, which of these contain more than 10 atoms per formula? So I've got A, B, C, and D, and then E is none of the correct. So let's see. This one's ammonium phosphate. Okay. This one is aluminum carbonate. This one is iron 3 cyanide. And oh, this is more than one. More than one, and this is none. So we only have to do those three to answer to see if these fit. Okay, we're looking for greater than 10 atoms. Greater than 10 atoms. All right, so we have to write formulas. So this one has ammonium. We did that one before. It's ammonium like that. It is a +1 charge. Phosphate, 3- charge, right? So balance the charges. We need 3 positives to balance that one. Okay. How many atoms are in that formula? We got 12 here, right? And 3 more is 15. 15. So we don't even have to count the rest of them. That one's greater than 10. How about this one? Aluminum carbonate. All right, carbonate's 2-, aluminum is 3+. So when you have a situation like that, the best thing to do is cross multiply. Let's take the 2 over here. Take the 3 over there. And you check yourself. 3 times 2- is 6-, 2 times 3+ is 6+. So we're balanced. Now we have 3 times, how many we have in here? 4. 3 times 4 is 12. There's another one. Iron 3 cyanide. So there's iron. There's cyanide. This is a 3+, right? So we need 3 of these groups, because that's a polyatomic. So 3 times 2 is 6, plus 1 is 7. Not enough. It's only 7. So more than one, yeah. More than one is correct. 2 of them, as a matter of fact. So in order to answer this question, you got to be able to do 2 things. Write the compound and count atoms. All right, so, okay, talk about Lewis dot structures. Remember those?
Yes.
Okay. So we're going to do one of those. Which of the following, A, B, C, D, would have 10 electron dots in its structure, both bonding and non-bonding? Okay, so we count all of them. So here are our choices. Okay. Remember the steps for writing a Lewis dot structure. You count up all the valence electrons. So there's 1 here. How many there? 4. 1 plus 4 is 5. Nitrogen is how many? 5. Because it's 5 from the left. 5, Roman numeral 5A. Okay. So it's 5 and 5 is 10. 10 electrons. We'll do that first. We're going to set up a assembly line. How about this one? Got 2 there, and oxygen is 6, isn't it? So this is 8. How about this one? Nitrogen is 5, just like that. 5 and 3 is 8, right? How about this one? 2 oxygens would be 12, and 4, 16. 16 electrons. Okay, now that we know our valence electrons, we build a skeleton structure. In this case, cyanide's in the middle, nitrogen's there, hydrogen's there. So you've used up 2, 4. We've got 6 electrons left, right? And we work from the outside in. So we've only got 6 electrons left. And hydrogen's got all it can handle. Right? So we're working from this side. So we have 6 electrons. We have 1, 2, 3, 4, 5, 6. Okay. We've got all our electrons placed. Now we could go ahead and make the octet. That's the next step. Make the octet. But the question says, how many contain 10 electrons total? Well, that one does, right? We don't even have to finish the dot structure. And if you're taking a test, you want to get it done quick, move to the next one. So in order to make the octet, we'd have to do this, right? Put those 2 over here, those 2 over there, and then you'd have this, that, that. But you still have 10 electrons. 2, 4, 6, 8, 10. Okay. But you don't have to go that far unless you want to. But to answer the question, this one has 10 electrons. Actually, we've already answered it. Right? Because that's 8, that's 16. So, okay. Rather than write the Lewis dot structures, then you just answer the question. Sometimes that's the hardest thing to do, is to find out what's the question. Or if you're like me, you know what the question is when you start, by the time you get halfway through, you forget what the question is. So you go back and read the problem. Okay, so let's move ahead, especially since I'm racing the clock. How about this one? This is my number 20. The total number of non-bonding electron pairs present in the Lewis structure of this compound. Right? And just to keep myself straight, we're looking for the non-bonding pairs. The number of non-bonding electron pairs. Okay. So we start off and do our Lewis dot structure. Silicon is same as carbon, 4. And then you have 4 here, so that's 8 total valence electrons. And then we say, okay, we're going to have silicon and hydrogen placed around it like that. That was an easy one. You can't put hydrogen in the middle of anything because it can only form 1 bond. So this one's an easy setup. 2, 4, 6, 8. That's it. We're done. Used them all up. Non-bonding pairs is 0. Okay. And there are 1, 2, 3, 4 bonding pairs. In case that question comes up. All right. This one's a little more difficult. Fair warning. We're looking for a coordinate covalent bond. coordinate covalent. What that is, normally when a covalent bond is formed, electrons are contributed from both atoms. But in a coordinate covalent bond, both electrons that occupy the bonding pair come from one side, come from one atom. So once the bond is formed, you can't tell. Right? They look just like any other compound. But if you can construct the compound, and you could propose whether it's a covalent or not. So we have these choices. HCN is this one. C is this one. And D. Okay. Dinitrogen monoxide, nitrogen, carbon dioxide, and hydrogen cyanide. So in order to tell whether you've got a covalent, you look at the Lewis dot structure and where it possibly could have come from. This one could have come from the cyanide polyatomic ion plus a hydrogen, which would have been, this would have been a -1, and this would have been a positive, so that's possible. But you also look at the construction of the Lewis dot structure. Which ones, if you take away one of the outside atoms, did you have an octet before or after that? You have an octet before, do you have an octet after? So if we take away this one, where are those two electrons going? Here's another clue. Test taking technique. You got these to choose from. Look at these two right here. But they're similar except for one thing. They've got this oxygen. This one's perfectly happy. That's nitrogen in the air. That's what we breathe. It's got a perfect octet, and it also has a couple of non-bonding pairs out there. So if this oxygen comes in, and oxygen has 6 electrons, right? It's valence, so it needs 2 more. So oxygen comes in, and it's only got 6 valence electrons. It comes in, it takes that one. There you go. So that seems the most logical. If you look at this one and then that one and say, okay, that was probably coordinate. We can't say that as easily about this one unless we say, all right, what about, what if we take away an oxygen? What do we have? Carbon monoxide. So carbon monoxide is what? It's actually like that. So if we have 4 and 6 is 10, so we have 2, 4, 6, 8, 10. And we could come in with another oxygen like that, make that bond. So I guess technically speaking, this could be coordinate. This is a better choice, I think. And when you've got a multiple choice question in a test, choose the best answer. And I think this one fits better than that one does. I don't think this one fits at all. Of course, that one's not. That was a toughie, I'll admit it. Let's see. All right, instead of doing working a problem, let's just look at polar molecule. Maybe we'll come up with some examples. What are the conditions? Well, I mean, what do we mean by polar molecule anyway? Well, first of all, is a polar molecule ionic or covalent? It has to be covalent. Because if it's ionic, then you don't have a molecule. Right? You have ions in a lattice. Okay, that's the first clue. Polar molecule. So it has to be covalent. It means you have covalent bonds, you're sharing electrons. Now, how do you make it polar? Well, what's polar? Polar is if you have an uneven distribution of electric charge. You don't have a complete ion. If you have an ion, then electrons are transferred completely from one place to another. But with a polar molecule, you have a slight redistribution of electric charge to one side of the molecule versus the other side. And the symbol we use for that is that delta. Just a slight difference. So if this is a molecule, and you have a slight redistribution of electric charge, this would be polar. It would be slightly negative on this side, slightly positive on that side. And why is that important? That determines how molecules interact. Right? Electrostatic attraction determines how molecules interact. If they're nonpolar, then they're less likely to interact. In other words, the attraction will be less. So now that we know what polar is and we know we've got a molecule, what are the two conditions that determine the polarity of a molecule? One, bonds. Bond polarity. The bonds in a molecule must be polar. For instance, water. Oxygen pulls harder on electrons. It's more electronegative than hydrogen is. So we give it this type of a symbol, an arrow with a plus that says the electrons want to move that direction. Okay? That means the bond is polar. So we have polar bonds. Then what do you need? If you don't have polar bonds, then you can't have a polar molecule. But if you do have polar bonds, that doesn't guarantee a polar molecule. Why? Because if these were out here opposite one another, their polarities would cancel. It's math. So the other condition is geometry. Polarity of the bonds and the geometry. So in the case of water, you have both of these redistributions taking place on that direction and that direction. So we do what we call vector addition. This is a vector because it has both magnitude and direction. Add them together, and that molecule is polar. Water molecule is polar. In the case of this one, 2, 4, 6, 8. 2, 4, 6, 8. Carbon dioxide. Carbon dioxide is linear.
That cancels.
Yes. It tends to have a polar bond this way and one on that side that way, and they cancel one another out. Okay. Let's see. Okay, how about this one? When we look at the electronegativities of bonds, if you form a bond between lithium and oxygen has a electronegativity value of 3.5. And lithium has an electronegativity value of 1.0. Now, what is that relative to? Well, there are several systems for determining and designating electronegativities. That is, how strong does an atom pull on electrons? And the one we use most often is the one invented by Linus Pauling. So the highest electronegativity on the periodic table is fluorine. It has the strongest pull in any kind of bond. It has to be in a bond in order to determine electronegativity. So if you compare electronegativities of these two atoms that are in a bonding situation, the way to tell if it's nonpolar, polar covalent, nonpolar covalent, or ionic is what's the difference between the electronegativities, because there's a battle going on. This one's pulling real hard and this one's pulling not as hard. So what's the difference there? The difference is 2.5. Okay. And anything greater than 2 equals ionic. Okay. So that would be, this would be an ionic bond, actually. And it would be more correct to say 2 minus 1 plus, and they just attract one another by electrostatic charge. Now that's not the complete molecule, I shouldn't say molecule, that's not the complete formula, because that's +1. Yeah, that's +1, this is -2. So there has to be another lithium over here to balance the charge. If you're going to write the complete formula, you would have 2 lithiums and 1 oxygen. But that is ionic. And that's how we tell it's ionic, is the difference in electronegativities. Okay. Okay. How about this one? If you're given this formula, what's the molar mass for that? If we have a mole of them, but if we only have one molecule or one formula, what's the mass of that? You add up the individual masses of the atoms. Nitrogen is 14.01. Multiply that times 3, right? Because you got 3 of them. Hydrogen is 1.01. But how many do you have of hydrogen?
Well,
And then we have 1 phosphorus. Let's see, I have to look that one up. 3097. Okay, and we have 3 oxygens, 16 each. And you just add those together. And that gives you both, if you're in atomic mass units, that's the number of atomic mass units for that formula. Okay. And let's see, I've got the answer here, so I don't have to calculate it. For that group of atoms, it would be this many atomic mass units. But since we learned about the mole, that value can also be molar mass. So if you have a mole of these formula units, which would be how many? Avogadro's number, that's a hint. It's big.
Oh, sorry.
Starts with a 6.
What's the guy's name, the avocado guy?
Avogadro.
Felix.
Yeah, Avogadro.
Okay,
6.022 times 10 to the 23rd.
that's the mistake.
That's a mole. If you have that many of these units, then it will weigh that many grams. All right. Let's see. All right, let's do this one. We just set up the problem. We're not even going to calculate it out. Just put it together. How many atoms are present in 10.4 grams of silicon? We want to know number of atoms. Okay. So what are our steps? We don't have a conversion factor that would go straight from grams to atoms. But we do need to get mass to numbers of some kind. And the magic number is molar mass. 10.4 grams. We can convert that to moles with our molar mass. So silicon is what? 28.09 grams per mole. That takes care of the grams. Now we're in numbers, and we can convert moles to numbers of atoms, right? And there's that magic number again. Right? And that sets up the problem. And if you really want to know the answer, you say 10.4 times that number divided by this number. And we just followed our units, dimensional analysis, make sure we cancel the units in all our conversion factors. And that'll give us the number of atoms in that mass of silicon. Okay. How many significant figures are we allowed to keep in the answer? 3, right. Okay. Okay, let's see. Okay. Let's do this one. Suppose you have this compound. The question is, what is the molecular geometry? Okay, where do we start? Well, first of all, you need to know the Lewis dot structure to say anything about the geometry of the molecule. So we have to do the Lewis dot structure first. All right, so we have 2 electrons here. Sulfur is how many? Same as oxygen, 6. 6 electrons. So we have 8 electrons. We have sulfur in the middle. Okay. So that's 2, 4. And we have 4 electrons left over. We can't put them out here, so we put them in here. 1, 2, 3, 4. There's our Lewis dot structure. Now, do we have octet duet compatibility? Yeah, hydrogens have their duet 2, 4, 6, 8. Okay, we're done with the Lewis dot structure. Okay, next. Remember the model that we use? Starts with a V. Remember that? Valence shell electron pair repulsion. which just means that these bonding electrons and these lone pairs are going to try to get as far away from each other as possible. Okay, so we need a regular geometric structure, a shape, that will put these electrons far from each other. And if you've got 4 of them, the regular structure, the geometric structure, is the tetrahedron. Right? The tetrahedron looks like, well, it's a triangular base. Right? Like that. It's a triangular based pyramid. Okay? So how would it be? Well, the sulfur would be in the middle. Right? Sulfur would be up here somewhere. And then we would have a hydrogen back here, maybe, and a hydrogen over here, and a pair and a pair. Okay. So the electrons are as far apart from each other as we could possibly get. That's a tetrahedron. Now, but that doesn't answer the question. This is the electronic geometry, where you're considering all the electrons together. Molecular geometry is you forget about those. Those lone pairs don't count in the molecular geometry. Now what do you have? Well, if you connect this one and that one together, let's rotate it a little bit. Now, if you cover them up, you have a bent molecule, or some books say angular. Okay? Same as water. Water's like that too. So you remember when I gave you the number of pairs, lone pairs or bonding pairs, doesn't matter. Actually, it's not pairs, it's groups. Groups of electrons. If you only have one group, it's only one possibility. Geometry. Now this is the electronic geometry. You always have to do that one first. Electronic geometry, then you cover up the lone pairs and you find out the molecular geometry. So if you have one pair, it's always linear. Or one group. If you have 2, then that's also linear. If you have 3, what's a regular geometric structure that puts everybody as far apart as possible? Uh-huh. It's a planar triangle. It's like an equilateral triangle. Like that. That puts everybody as far apart as possible. And then we did this one already. So if you have 4, it's a tetrahedron. Okay. Then when you get down to 5, it gets a little more difficult. In this one, you go back up here and say, this is in the middle, our triangle. And then we've got one up here and one down here. So it's a triangular pyramid. Okay, so you have your that, and then you have up here, and then down here. So 1, 2, 3, 4, 5 positions. That's as far apart as you can get. And then the last one, I never go higher than this one. 6th is an octahedron. An octahedron is like you replace this one with a square in the middle. And that's 1, 2, 3, 4, 5, 6 positions. Now that's the electronic geometry. In order to go from that to molecular geometry, you find your lone pairs and just cover them up and say what's left over. So we're still right. Okay. All right. Let's see. How about this one? The atomic masses of these two elements, well, we'll give it to you. 4 here, and beryllium is 9.01. Those can be atomic mass units, or they can be grams per mole, molar mass. Okay, get those straight off the periodic table. Which of these following statements is true? 1 mole of beryllium has more atoms and 1 mole of helium. Is that one true? When you step back and look at the definition, that's a stupid statement. A mole is a mole is a mole, right? It's the same number of atoms no matter what it is. A mole is just a number of something. So that was false. You can't have more atoms when you have 1 mole of each. They're the same numbers. Okay, how about this one? A mole, 1 mole of helium is heavier than 1 mole of beryllium. Is that true? You have the same number of atoms, but each one weighs differently. Then you can say something about the mass. Right? If you have a mole of helium and a mole of beryllium, how much mass do you have? Well, for this one, you have 9 grams, and for this one, you have 4. So that's exactly the opposite. It should be the other way around. Yeah. So that was false. Let's see. C. 1 mole of beryllium same number of atoms as 1 mole. That's a true statement. Because that was the argument we used to make A false. When you have a mole of something, it's always equal to the same moles of something else. Okay? Let's see. Oh, we haven't balanced any equations yet, have we? That's part of this whole operation, isn't it? Let's try this one. All right, we've got okay. Methane, and in some kind of reaction, it produces C3H8, which is propane. Same stuff you burn in your barbecue. Okay, so this is going to produce that plus excess hydrogen. Right, we want to know the coefficients here. So remember our budget method? Carbon, hydrogen. Oh, that's it. We've counted for all the elements. On this side, you have 1 carbon and 4 hydrogens. Okay. That's how you start. You start, where are we starting from? On this side, we have 3 carbons and 8, 9, 10 hydrogens. Okay. Now, to balance it, just pick a place. Well, remember one of the tricks. If you've got an element standing alone, do it last. Because any coefficient here is only going to change that. And you don't want to get to the end of your balancing and stick a different number over here, and that changes something else, and then you just keep going around in a circle. So we'll save hydrogen for last. That means we'll do carbon first. So if we need 3 carbons, how do we do that? Coefficients only. You can't change the subscripts. Once you've written these elements and compounds correctly, then the only way to balance it is with coefficients. So this gives us 3 carbons and 12 hydrogens, right? Okay. Now we can balance the hydrogens. How many do we need? Well, we don't want to mess with this one because we've already got our carbons balanced. So we balance our hydrogens with that one. But how many do we need? Well, we need 12, but we've already got 8. So 8 and 12 is 4, right? So we need 4 hydrogens. And that should give us 12. Let's see if it works. 4 there plus 8 is 12. Okay. This is 3 times 4 is 12. 3 carbons, so we're balanced. All right, now what are the coefficients? 3 and what? 3, 1, and 2. Don't forget this one. Just because there's no number there, we don't write the 1 in there. Because if you've got that there, you got to have at least 1 of them, or you wouldn't put it there. Right? We don't write that in there and say, oh, by the way, we don't have any. That's kind of stupid. If you got the formula there, there's 1 of them. So the coefficients would be 3, 1, and 2. Okay. And the only way to get good at balancing these things, do a lot of different ones. Let's see. Looking for stuff we haven't covered yet. Be sure to cover all our bases. Okay. How about this one? Given this electronic configuration, okay? The question is, how many valence electrons are in that atom with this number of electrons in those positions? Think back to the definition of valence. It's the highest energy electrons that are in the same period, in the same principal quantum number. We talked about that, didn't we? The N, principal quantum number. So look, can't be 1s, can't be 2s, they're full. 3s, but we haven't got to the highest one yet. There's 3 here, but look, there's 4 there and there's a 4 there. So 2 plus 3 is 5 valence electrons in that configuration. Okay. The confusing part here is to pull those 10 in with these also. But these are not valence electrons because this is a lower energy state. It's a lower principal quantum number, I should say. Actually, this is a lower energy state than that one, and it's a higher energy state than that one. That's why we write it in that order. But when we're talking about valence electrons, we're talking about principal quantum numbers. So that's 2 plus 3 is 5. By the way, is that one full? Yeah, d orbitals take 10 electrons. So it's got all it needs. That one's full. That one's not. P's can have 6. Okay. We're doing good. Let's see, I've got another one that can talk to us a little bit. How about, let's balance another equation. The reason I want to do this one is it uses a different, I guess you could call it a trick. So if we're starting off with this one. Oops, not O, H. Go. This is butane, right? The little lighters, butane lighters, that's what they put in. And then when you flick that flint, it combines with oxygen and produces carbon dioxide and water. Okay? So we've got carbon, hydrogen, and oxygen. That covers everything. Count them up. 4 here. Let's see, hydrogens, 10, and 2 oxygens. On this side, we have 1 carbon. Hydrogen is 2, and 3 oxygens. Right? Don't panic. Just because we have an even and an odd here doesn't mean it's always going to be that way. We're just getting started. Okay, so which one we balance first? Well, we definitely don't want to touch oxygens because we have an element here. Right, so leave oxygens to last. We could start with hydrogens or we could start with carbons. Personally, I'd rather start with carbons. So in order to have 4 carbons, we need a 4 here. But that also changes the oxygens. So that's 2 times 4 is 8, 1 is 9 oxygens. Okay. Went from bad to worse. Okay, how about hydrogens? Right. We have 10 hydrogens here. To get 10 hydrogens over here, we put a 5 right there. Right? But that also changes the oxygens again. So 5 plus 8 is 13, correct? Okay, carbon, hydrogen are balanced. Now we got to do something with oxygens. So here's the trick. You have to come sign in. There's no whole number that we can multiply here that will give us 13 oxygens. Right? So we're going to use an intermediate step, which is a fraction. Thirteen halves will give you 13 oxygen atoms. Right? Think about it this way. You have 2 oxygens here in that molecule. And let's take half of that and times 13. So there you go. You got 13 oxygens. But we need to go to the nearest whole numbers. Right? So we need to get rid of the fraction. So how do we get rid of the fraction? Multiply by 2. That'll cancel the fraction. Okay. And once you've got, this is balanced just like it is. It's just not in the form that we prefer. So in order to balance it, we'll get rid of that fraction, but we have to multiply by the same number of everything. The ratio is fixed now that it's balanced. So we have to do like any mathematical equation, If you multiply one side by 2, the other side's got to both multiply by 2. Everything has to be multiplied by 2. So that means 2 here, that 2 is gone. This is 8, and this is 10. Okay, so the coefficients for this one would be 2, 13, 8, and 10 to the nearest whole number ratio. And if you think, is there a way to simplify this? No, 13 is a prime number. You're not going to divide anything into that. That will decrease the whole numbers. So that's it. 2, 13, 8, 10 would balance that equation. Okay, let's see. All right, one last one. Given this balanced equation, that's ethane. What type of reaction is this, by the way? Have we covered that yet? It's a combustion, correct? Did we do that before? Whenever you react oxygen with something, it's a combustion. Maybe we didn't get to that in this class. Anyway, that's not the question. Question is, if you start with, let's see, where am I? You start with 2 molecules of ethane. How many molecules of oxygen do you get? That's 2 molecules of this one. How many molecules of oxygen are required, I should say? 7. Okay. That ratio is fixed for the balanced equation. 2 molecules of this will react with 7 molecules of oxygen to give you 4 molecules of carbon dioxide and 6 molecules of water. Okay, if you think about it on the molecular level, if you get down small enough, you can see these 2 molecules floating around. They encounter 7 molecules of oxygen. Boom! They give you 4 molecules of CO2, 6 water. Or you can think about it in terms of moles. If you have 2 moles of this one, 2 times 6.022 times 10 to the 23rd, and then you have 7 times 6.022 times 10 to the 23rd of these, they get together, they produce 4 times Avogadro's number and 6 times Avogadro's number. The ratio is still the same. That's how we look at balanced equations in terms of numbers of molecules based upon the coefficients. So we've been balancing these equations for a reason, because that establishes the ratio, the nature of the reaction itself. That's why chemists in 1860 had no idea why their reactions were going crazy. Companies were losing money. So they met at that small college in southern Bavaria, Karlsruhe. They said, we're going to figure this out. Because all they knew at that time was mass. Mass, 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 mass. And that was not the answer. The answer was moles, numbers of atoms and molecules. That solved the problem. And now we benefit from their hair pulling. Okay. Well, is there anything that we need to talk about that we haven't? Or we want to go in the lab and have some safe fun?